Hello, I'm JW. This time I'm going to have a look at Autotransformers again, and really how these things actually work, the sort of thing they might actually be used for, and also going to have a look at that old one which was featured in a previous video, and to see what sort of voltages we can get out of it. Now, transformers work on a principle that if you have a conductor or a wire and you pass a current through the wire, then you get a magnetic field created around the wire. And of course, if you take the single wire and coil it up, so you've got many hundreds or even thousands of turns, then that increases the magnetic field accordingly. And if we draw a typical transformer here, then basically all it is on one side is just a wire that's coiled around many hundreds or even thousands of times. And there's usually some kind of central core made out of steel or iron or some other ferrous material. And that's really what the wires are wrapped around. Now, the other property which is important here is the fact that if you have a magnetic field and you move a wire through it, then that actually generates a current in the wire. So that's sort of the reverse thing. Now, of course, in a transformer, the wires are actually fixed, but if you put AC through this, as in alternating current, then that's essentially a moving magnetic field. So what you can do is on the other side, put another coil of wire. And although this is fixed in position, because you've got a moving magnetic field because of the alternating current going through this side, you actually get a current in the winding over here. As having the magnetic field moving, whereas the wires are stationary, is pretty much the same deal as if the magnetic field was stationary and you were moving the wires. So moving magnetic field here, and that creates a current in the winding on the other side. And these are generally wound around the same core in the middle, or in some cases it's sort of a open or a U-shaped core or whatever, and then there's two separate coils, but either way they're linked magnetically together. Now, transformers don't work with DC because if you put DC in here, you would only get a fixed or static magnetic field, and then of course nothing's actually moving or changing, so hence transformers only work on AC. Now, as we've got here, this coil here has a lot more turns or coils on it than the one over here, and for example, we say this one had, let's say, 1,000 turns there. This one over here might say only have 100, so it's considerably less. And on the side over here we can attach a voltage, so I'll say in this case it's the mains voltage in the UK, so 230 volts, and that's between these 2 points, so we're going to call that the 0 at the bottom there, and if that was a supply that would be called the line and the neutral. Now, because we've got different numbers of turns here, what happens here is there's an effect of either dividing or multiplying what we've got. So in this case, we've got 1,000 here and 100 here, so it's a factor of 10 difference. So 1,000 divided by 10 is, of course, 100. And it turns out that whatever voltage you've put in over here, so the 230, as we have 10 times fewer here, it's dividing by 10. Then the voltage on this side is also divided by 10, so the voltage here would be 23 volts. And again, that would be the 0 at the bottom as well. So 23 volts between these two terminals. Now, as well as voltage being divided by 10, a similar effect also occurs with the current, and the reason for this is so that the power, which of course is voltage multiplied by the current, remains the same on both sides. Because of course if we had a different power on each side, that would imply that there was a huge amount going away somewhere, and that would end up with the transformer getting exceptionally hot. So if we connect a load over here on the 23 volt side, now we might say that that particular one is going to take a current of 5 amps. Then what we'd find on the other side, the current here, rather than being 5 amps, would actually only be 0.5 amps, because it's the same dividing by 10, so 5 divided by 10 is 0.5. And the reason for that is so that the power, which is basically the voltage times the current, should in theory be the same on both sides. So over this side it would be 23 times 5, and over this side it's 230 times 0.5, which of course add up to the same. And that of course would represent over here a power of 115 VA. It's not necessarily going to be watts in this case, because watt would imply that it was a purely resistive load, but it would be 115 watts if it was, say, a electric heater or something there, but 115 VA there. And it's actually the same over here, so 230 times 0.5 is that same 115 VA over there as well. So the power on both sides is the same, the 115 VA, but the voltage and current are different, in this case by a factor of 10. So 230 in, 20 out, so it's dividing it by 10 as we have fewer turns on this side, but the current on this side is actually 10 times greater, so basically it's dividing across in the other direction. 5 amps out there, only 0.5 amps in on the other side. And this is a theoretical model of a transformer, which would indicate that all the power here is going to show up on the other side. Now, in reality, transformers are not 100% efficient. They're pretty close, certainly in the very high 90s for most transformers. And the waste, in that case, would actually show up as the transformer heating up, as obviously these things are not perfect in reality. But ideally you want to keep those losses to a minimum. Otherwise, of course, if the losses were huge, the transformer would get exceptionally hot and eventually set on fire, and flames would come out of it. Now that's a normal kind of transformer, and an important point about these is that there's no electrical connection between this side and this side. It is literally just one coil of wire there and an entirely separate coil of wire over there, and they may be separate like that, or they may be wound on top of each other on the same iron core. Various different designs available, but there's no electrical connection. So if you touched either of these over here, you would not get an electric shock, even if this was, say, 500 volts over here. Because this was a different arrangement, you still wouldn't get a shock here because none of these are referenced to ground. But of course on this side the normal main supply is referenced to ground, so if you grab hold of the wire up there, then you most definitely will get a shock. Now autotransformers work on a similar principle, but they have one big difference in that there's actually only one winding inside. So just get rid of all of this business here, and then we'll see how one of those would work. So an autotransformer has the coil as we've got here, so it's the same one we were using before. And again, in this case we can apply, say, the mains voltage to it, 230 volts. And there is also that iron or steel core or whatever in the middle, just not showing that here, so it'll be easier to draw otherwise. And an autotransformer, instead of just having the two connections at the ends of the winding, it also has extra connections part way along. So we can draw some of those in here, so a couple of them in there like that. And we can put one to almost right at the top there. And of course you can also continue these exact same wires across as well, just to make it easier to draw things in. Now if you connected something on this side to the bottom here and the top up here, then of course you just get the 230 volts that you're putting in, because it's just the same basic wires going through. You're not actually using the transformer at all. So at the bottom here we can call this the 0 volts as before, and again the 230 at the top, so nothing really changes there. But if you were to connect to one of the other terminals, then you'd find that you've actually got different voltages. So this one here might, say, be 100 volts, this might, say, be 160 volts, and this little tiny piece at the top, you might find that will say 220 volts. So if you connect between the 0 here and this one, you would get 100 volts output. So a piece of equipment that needed 100 volts, connect between these two terminals. Or if you wanted 160 between here and here, and again the 220 between there and there. So it gives you a number of different options to change the voltage into something else. And although it's the same winding, it is using the same principles as in the other transformer, as in it's a magnetic arrangement. So you will get, in theory, you could have more current coming out on the 100 volt setting than was actually going in on the 230. So again, they're fairly efficient devices, although of course in reality there are some losses, because of course these things do heat up a little bit. Now the main difference here is that there is no isolation at all. So unlike the previous example, if you were to grab hold of this 220 volt piece here, then you would definitely get a shock from that, because all of this is still referenced to ground, because the input is referenced to ground, as the main supply always is. So all of these terminals are fairly dangerous items. You would definitely not want to be touching any of them. No isolation whatsoever. It is literally just changing the voltage to something else, but it's still referenced to ground on the output. So definitely not something you want to be using to improve safety, because it definitely won't do that. Now, as well as connecting between these various terminals, there are certain other things you can do. So, for example, if you connected a piece of equipment in here between these terminals, then the voltage we get between those would be around 60 volts. So, although we're not connecting between the bottom here and the top, we can connect to any of the others, and you'll get the difference between the two. However, this is still fairly dangerous to touch there, because even though there's only 60 volts there, you've still got 160 there and 100, so touching either of those is still going to be very dangerous. So it's certainly not a safe thing at all. And another example of that would be if you connected something up here between these two, then the voltage you would find there would be 10 volts. So if you had something that needed only 10 volts to operate, you could certainly connect it between those two. But again, don't be fooled thinking, oh, it's only 10 volts, that's perfectly safe, because it's not. 10 volts between them, but if you touch this one relative to ground, then it's 220, and that one is still 230. So touching that would certainly be extremely dangerous and not desirable. But as long as you're only connecting between two, say for a lamp or something, then it is the 10 volts that you've got as the difference between two. Now, Autotransformers, the main advantage is there's only a single winding, so the cost to manufacture is considerably less because, of course, there's only one large piece of copper. If you had two of those, of course, it would be considerably more stuff involved, and it would be more expensive to manufacture. And you can also use these in reverse. So, for example, if you wanted to change the voltage, say from 100 volts to 230, you could put 100 volts in on these two terminals, and then you would get 230 volt out over here. And in theory you could put say 160 in there, or even put 10 volts in there, and in theory you would get your 230 volts out over there. But just as with the other transformer, the same issue with the current applies. So if you wanted to put a sensible load on the 230 here, although in theory you could put 10 volts in, the current you have to put in here would be absolutely huge, even just to get a fairly small current out there. So there are practical limitations, but certainly in theory any of these will give you the same voltage on the other side. Now, there is a variation on this idea, and this is a piece of equipment we've seen in other videos. So you can have a fixed connection here at the bottom, and instead of having various points being tapped off, you can have the whole winding arranged in such a way that you can have a moving contact, which can therefore move to various positions depending on what you've got. And we can just put that in here, say as a block of material there, and then a wire coming off. So this then can be moved in either direction, sort of up here and down here. So the voltage you then get out of here can be adjusted. So if you move this all the way down to the bottom, you're going to get a very small voltage between these, and as you move it to the top, again you'll get a fairly high voltage. And we've seen this in a previous video, and these things are generally referred to as Variacs. That's actually a name owned by some company or other, much like Hoover and vacuum cleaner. But Variac basically is a variable transformer. So same idea, it is an autotransformer, and therefore there's no isolation. But of course, instead of having a fixed one, it's just a movable block, usually of carbon or something, along the winding, so then you can select various voltages. And in this configuration, it would only give you between 0 and the 230 on the input. In most normal circumstances, Variac's configured so you can actually go above that. The way that's done is to have, on one side, they've got the wire coming in here. The 230 volts is actually applied in the point in the centre of the winding somewhere, and therefore if you move this sliding piece here, once it's level with that one you get the 230. Anything below that is less than 230, and if you move it over the top here, then you actually get more than 230, and it's fairly common that the top piece here would be around 270. So then you can have a, say, 230 input, and the output is variable from 0 all the way to 270 or so. So that's how transformers and autotransformers and also Variacs actually work. And by just adjusting the various connections to them, you can of course get all kinds of different voltages out of them. Now let's try those on the actual transformer itself. So what I've got here is the two grey leads are the power supply, so that's the 240 volts or whatever it is today. And then we're going to check the voltage between various terminals. So I've got the red lead here, so you can just check the voltage displayed here. And then the other lead multimeter is this black clip lead that we've got on the in neutral input here at the moment, and power comes in from the connector block. So let's just try this out. And to start with, we're going to be connecting the mains input to the alleged correct terminal, which is marked 245. So we should get the actual voltages marked on the other ones. So power's on, and we can now just check out some of the various voltages. So first of all, let's just see what the actual incoming voltage is. So today it's about 242 or thereabouts, so it'll just vary a bit with things here. So 242. Now this is marked 260, and that's pretty much what we're getting. So 256. We're getting slightly less because obviously we're not putting 245 in. Over here, for example, we've got say 196, so that's the 200 tapping. And then over this side we have some lower ones, so this should be the 135. So again, pretty fairly close there, so 133. So the 115 here, again pretty close there, and the 105 on this one. So as you can see there, they're all giving us approximately the correct voltage. And it's important to realise again that this is not isolated from the main, so although this may be a lower voltage here, it's still referenced to ground, so if you were to touch any of these terminals, you would get a dangerous electric shock from them. Now just alter this, so we've got the incoming supply now is connected to this terminal, and this is actually marked 215, but of course the voltage we're going to be putting in is still the same, the 245 or whatever it was previously. So what we should now find is that because we're putting essentially the wrong voltage in here, all of these will also be higher than they should be. So 215 is sort of equivalent to 40 or so. So these of course will not be what they're claiming, and we should find at the end here the 260 is actually considerably greater than 260, and the same will apply over this side. So again, the 105 will not be 105 in this case. We should see that those are actually higher. So let's just try that one out. So again, transformers on, so we'll just check the voltage on the actual incoming again. So again, it's at 242 again, pretty much what we had before. And if we just say go to the 260 terminal now, we should find that's quite a lot higher. So yeah, there we go, it's 291. And that's because we're putting a higher voltage in at a lower point there. So the ratio between the terminals is still the same, but because the input voltage is considerably higher, of course the other terminals are going to be higher as well. So 290 there, and if we come over here, this should be 135, but as we can see it's actually 150, and then over here, so 105, we're actually getting 118, and the same applies to all the others. So over here, for example, so that's about 260 now, so basically they all increase if you put that there. And if we moved the incoming supply to the 260, we would find that all of the terminals then were a lower voltage than they actually claimed. So here the main's going on the 260, tapping there. So if we check that one, we'll find that it's same as before, about the 242, and then we should find all of these are lower. So if we say go over to the 200 one here, yeah, we see that's about 186, and so over this side at 135, and that's 126, and the 105 is actually around 98. So there's no real magic here, it's just the same ratios between all of the terminals. And of course, if you put a higher voltage or low voltage in to the various places, then all of the other terminals would again be lower or higher in the same ratio. Now I've moved the connections back to the correct voltage points, that's the 245 input, but this time we're actually measuring between the red probe here and the black lead over there. So I've actually moved that up onto the 200 volt tapping. So we've still got the mains voltage coming in, and of course all of these are still live, and if you touched any of these, then of course you would get a dangerous shock from them. But if we actually measure between that black one over there and this one, say on the end, let's see what we get. So we've got 200 there, 260 here, and if we check the voltage here, then we're getting around 60 volts, or 59 in this case. So again, it's the same ratio between the terminals. Because we're measuring between those two rather than across the whole thing, we're only getting the voltage difference between them. And again, if we went to this one here, which is the 215, then we're only getting around 15 volts or so. So basically it's 200 and 215, so 15 is the difference between them. And the same thing also applies over here. So if we go down, say, to the 105, we're going to get about 92 volts there. So in theory the difference should be around 95 there. Basically it's 200 minus 105. And if we go to the 135, 200 minus 135, and we're getting the result approximately 65 volts there. So it's slightly lower in this case. But the principle is again the same. It's just depending on the actual ratio between the various points, and that's the kind of voltages you get. So in theory you could connect something there which only needed 15 volts. But the important thing to remember there, if you did that, although you've only got 15 volts between the two terminals, you're still referenced to ground. So if you were to actually touch those terminals, one of them is going to be at 200 volts and the other one is going to be at 215. So in either case, touching either of those would give you a fairly severe electric shock. So don't be fooled by the fact there's only 15 volts between them. It's actually 200 and 215. So look there at the Autotransformer and also the kind of voltages you can get out of it. And they're fairly commonly used to convert voltages, say, from one country to another. I believe that one, according to the person I got it from, said it was used to convert to 120 volts because they had a number of appliances they'd brought with them from North America, and that's a fairly common use for those things, and you can actually buy those still now with the appropriate sockets and plugs already attached for the various countries. But the main thing to remember is they're not isolating in any way, so what comes out of it is just as dangerous as what goes in on the other side. And of course they don't change frequency either, so put 50 Hz in one side, you're going to get 50 Hz out the other. Now that particular transformer we will be seeing again once the case has been repainted and various other items acquired for it to replace that gigantic hole on the front panel. Some of those components are coming from far away, so it could be a couple of weeks before we get round to that one. But until next time, thanks for watching.